Hi, this is Sung. I'm your online maths mentor, and in this episode, this topic, it's a brand new topic, we're going to be looking at applications to the physical world. Now, we covered that pretty much in the 2-unit advanced course, and we looked at motion. We started looking at motion, and we're going to continue that in the extension 1 component. And in particular, what I want to do is look at a concept called projectile motion. All right, now what is projectile motion? Well, if you've ever played any games like Angry Birds or whatever, you'll know exactly what projectile motion is, right? Or if you've ever played football or whatever, you'll know what projectile motion is, because projectile motion is what happens when you throw objects, all right? Or project objects, right? So I'll give you an example. In this example here, we've got a cliff, right? And we're throwing something into the water. See how it follows like a parabolic arc, right? So it's the shape of a parabola or a curve. Yeah, that's exactly what projectile motion is. Another example is a person kicking a football, right? You like my stick figure. Basically what he's doing is kicking a football, and again, it goes in the shape of an arc, right? Or an upside down parabola, okay? So the important part when we're dealing with projectile motion, the important part to recognize is that we're dealing with 2 components of motion, right? So there is the vertical component, which is the up-down component, and we have the horizontal component, which is the left-right component. Now, we can break this down into another topic, which we call vectors, right? Now, what a vector is basically some quantity that both has magnitude and direction, right? So in this particular case, we can break down any sort of motion into its vertical component and its horizontal component, all right? So we have here, for example, displacement, velocity, and acceleration in its vertical forms, displacement, velocity, and acceleration in its horizontal forms, right? Now, do you remember, before I deal with how we break this down, do you remember how we move from one to the other, from displacement to velocity, from velocity to acceleration, and vice versa? Do you remember that? Well, essentially, let's look over here, because this gives us a reminder of how it works. Now, in the 2-unit course, the way that I drew it was flipped upside down with displacement at the top and acceleration at the bottom, but it really doesn't matter. Essentially, what's going on is this. You've got acceleration, right? To go from acceleration to velocity, you integrate. Yep. And to go from velocity to displacement, you integrate. So as you go from up here all the way to down here, you integrate. When we go from displacement all the way to acceleration, we do the opposite of that. Remember what the opposite of that is? It's differentiation. So we do that, right? So we're either integrating to go from acceleration to velocity to displacement, or we're differentiating our functions as we go from displacement, velocity, and acceleration. Now, the other thing that I wanted to point out in relation to acceleration, velocity, and displacement is that we are differentiating and integrating with respect to t, which is time. Okay? Time. Now, before we launch into any questions, I want to deal with how we break down a particular vector, or a motion vector, into its horizontal and vertical components, right? So let's go through that here. Imagine if we have an object being launched or projected at a velocity of v0, and 0 stands for when time equals to 0, so it's the initial velocity. So v0, when time is equal to 0, initial velocity. So we're dealing with when an object gets projected at v0 meters per second at an angle of theta degrees, right? Can you imagine that? So you've got a ball being kicked, thrown, launched, etc. at v0 meters per second at theta degrees, at an angle of theta degrees. What would its Vertical component B. Now, can you see the mistake? I can see the mistake. This should be y dash, and that should be x dash, right? All right, so what would be the vertical velocity, right? Well, the vertical velocity, we basically use trigonometry. We use SOHCAHTOA, right? And we can do exactly that, right? So we've got opposite versus hypotenuse and adjacent. Got it? So let's work this out. So you've got opposite over hypotenuse is sine. So you got sine theta is equal to y dash over v0, okay? Which means that y dot is equal to v0 sine theta. Got it? What would be the horizontal component? Well, we're using cos this time, cos theta, right? Adjacent over hypotenuse, x dot over v0, okay? Which gives us a horizontal velocity of v0 cos theta. Does that make sense? That's essentially what's going on. So now we've pretty much been able to work out what these two are at time equals to 0, at the initial conditions for that, given our initial velocity and our angle. Okay, so let me just write that down. So what I want you to notice is that the horizontal and the vertical components of the initial velocity, given its angle of projection, will be given by v0 cos theta and v0 sine theta, basically using SOHCAHTOA. Got it? So that's basically what's going on. Thank you very much for watching. In the next episode, we'll look at how we can get the acceleration and the displacement.